and let's go ahead and get started with our solutions to problem set 7. So let's go ahead and answer the question. So look at the stress strain curve below, which is stiffest, toughest, strongest, highest yield strength, most ductile, largest elastic strain energy, etc., 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 etc. So let's go ahead and let's do this. So stiffness, we know it's the kind of slope in this linear region. So this would be the slope here for that particular curve. So the stiffest is probably going to be this purple one. So number 14. Toughest, and also for the largest elastic strain energy, we need to know the volume for these materials. So realistically, we don't really know the answer to this, but we can kind of estimate it from this stress strain curve. So looking at kind of the data here, I would say probably 16 will have largest elastic strain energy. Again, assuming that the volumes are all kind of the same. And for the largest elastic strain energy, I would actually say it'd be SR. Let's see, what is it? 0, 0, 0. If you're assuming, again, because remember, it's the area under this kind of elastic regime, so that's a pretty large area. Again, there's going to be multiple arguments here. Again, that's why you want to explain your answers. What is the strongest? I.e., which has the highest ultimate tensile strength? Sorry, this is for this. Which has the highest ultimate tensile strength? Well, that would be my green curve here. So it'd be 16. So this is my ultimate tensile strength, the largest stress in each of the respective stress strain curves. So there you go. Most ductile. That would be the highest, essentially, strain at fracture. That would be my red curve here. So that would be, I think it's SR10. So most brittle, the one that fractures first. So it'd be this guy right here. So I think that's my kind of darker blue. So I think that'd be 18. So SR18. And then again, we've already answered that question. And so for the black curve, so we are going to label our 3 regimes. So for the black curve, it's here and here. So this would be 1, 2, 3, elastic, plastic, and fracture. This would be my Young's modulus, as we kind of said it here. My yield strength would probably be right here. My yield strain would be essentially right here. This would be my ultimate tensile strength is equal to my strain at fracture, and this would be, again, right here down below. That would be my strain at failure. Hopefully, we've kind of deduced that. Yeah. And again, in an exam, perhaps you might be asked to kind of write out the value. So that might be coming up. So a little bit of a hint. So let me, actually, what I'm going to do here, sorry. Quickly, I'm going to insert kind of a clean copy. So enjoy while I search for this Pset. So let's go through my files, not my personal files. Let's go into problem sets. You'll kind of see the kind of the fun process, as you can see, and no sarcasm whatsoever, the fun process of essentially inserting this into, and also need updating, but I'm going to ignore that. So let's get a clean sheet and let's kind of work through these problems together. Oops. All right. So let's look at number 2. So for the following stress state in KPA, draw the RVE element and be sure to indicate essentially a coordinate system. So we need to draw the Mohr circle. Actually, so let's go ahead and draw the RVE element. So I have a system like this. I have my cube here. So cube, cube, cube. So this is 1, 2, and 3. So I've got a stress in the 1, 1 direction out of the board. That is positive. I have basically a negative in the 1, 3. So again, sigma 1, 3. This is the normal, essentially, to this plane, and it would be acting in this direction. So if it goes like this, this would be negative because, again, it's going to produce around this axis, it's going to produce a clockwise rotation. So that is drawn correctly there on this other side. And then I'll also have a stress in the 3, 3 direction right here. So that's my RVE element. So then I'm asked to draw the Mohr circle for these different planes. So I'm going to go ahead and I want to kind of draw I'm going to use strategic. So I want to do this here. I want to do blue here. And I want to do green, this guy, this guy, this guy. So I'm going to draw my 1, 2 plane first. So 1, 2, Mohr circle. Here we go. So tau, sigma. So I've got 28 here. I've got 0 here. So I'm lying on this line. Here's my circle. So I'm already in my principal stress state. To get to the maximum shear, I need to rotate 45 degrees. So I think that's what it's asking for, the angle. So angle to get to principal would be 0 degrees. Angle to get a maximum shear, 45 degrees. Again, because remember, to go from here to here in 2 theta space, that'd be 90. So theta is equal to 45. And then finally, it's asking me, write the full stress state for a clockwise rotation of 57 from the maximum shear stress state. So I know from this original stress state, I need to rotate 45 degrees counterclockwise. So positive 45 degrees from here. Then if I rotate then back 57, my final change in rotation, so 57 clockwise, so 45 minus 57. So that would be that rotation to get there. So let's calculate that. And I could use my good old handy, actually I'm going to delete all this stuff except for here. So I'm going to delete everything else here. Notebook I was working with previously in an office hour. So let's go ahead and quit our kernel. I want to clear all my variables. Let's reevaluate. Let's do this problem together. So I know that for my stress, it's my S12 OG. OG is going to be equal to 28, 0, and 0. So I'm in my principal stress state because there's no shear stresses. So if I do T dot, and actually I can kind of figure out, it's a good kind of check here. So T dot S12 OG slash dot theta goes to 45. So this would be essentially the rotation I get, or you could do minus 45 as well to get positive 14. So, because again, that makes sense, right? Because at the center of my circle is 0 and 28. So the center is 14. So the radius is 14. So we're good to go there. So that's the rotations essentially that we're playing around with. So you can see here that the way that Mathematica is kind of looking at it, if it's counterclockwise, it's treating kind of that point. But again, it's circle symmetry. So it doesn't matter too much. So, but again, I'm doing 45 counterclockwise, and then clockwise is going to be positive. So it's going to be eventually 45 minus 57. So let's do this and look at this numerically. So this would be my value, or one of the one of the possible stress states. Again, you're going to be kind of connected to on a line. So that's it. So that's how you would answer that question. And you do the exact same thing for. You can see here that for my 1-3 plane, or my 2-3 plane, my blue here, it's a very similar type of solution. So 37, 0. Here's my circle. What's the rotation to get to principal? 0. I'm already there. What about maximum shear? 45. So counterclockwise, positive. Clockwise, negative. So I'm just going to do the exact same thing. I'm just going to do my S23 OG equals 37, 0, 0. Let's do T dot S23 OG slash dot theta goes to 45 minus 57. Let's look at that. And there we go. Now comes the hard one. So let's look at our basically 1-3 plane here. So for my 1-3 plane, so I've got my tau, I've got my theta, or sigma, excuse me. So I've got a point at 28 or 37, got a point at 28, I've got a point at 12 and 12, I've got a point here, 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 here. So I'm going to draw my circle. I want to look at this here. So I know that I have to go through this rotation of 2 theta to get to my principal stress state. So I need to figure out, because I'm not in my principal stress state. Because if I look at S13 OG, it equals this 28, 37, minus 12. So if that's the case, if I'm starting from this kind of point here, if I want to rotate to get to that principal stress state, I need to kind of figure out that value. So let's go ahead and let's do that. So I need to solve for what angle, S13 OG, what angle is going to allow me to make this, my third equation when I dot this, equal to 0. What angle? So I'm going to do numerically solve, and solve of this, set it equal to 0, theta. I'm going to solve it right here. And then I'm going to go right here. I'm going to pull out this equation. And then this is going to tell me where we're rotating from. So 34.722 degrees. So I'm going to rotate that amount, essentially, in order to get to that principal stress state. So I'm going to rotate a theta of that value. So I need to rotate that amount in order to get to kind of my problem. Now, the question here is asking, so once I know that, so that's going to be the 2 theta or the theta rotation to get to my principal stress state. And if I know that this is basically 2 times theta, you can kind of imagine it'll be 45, or, kind of, again, if we're in 2 theta space, 2 times 45, because again, I want to look at what's the rotation from here to here. Well, it'd be, again, 2 minus 45 times, let's go ahead and do 2 theta, for example, or you just do 45 minus theta. So that would be the rotation to get to maximum shear stress. So now I could take this angle and I could do, okay, to get to my maximum shear, I need to go clockwise. So I need to rotate basically this difference of 45 minus this in the clockwise direction. So this is now the rotation from my original stress state that I need to get to the maximum shear. But now I need to go 57 or minus 57 this. So that'll be my next angle here. So now all I have to do is do T dot S13 OG slash dot theta goes to here. And that would be the rotation to that 57, minus 57 degrees. So that's it. So our last question asked us to kind of draw the Mohr circle. And one of the things that we kind of actually, we didn't do here because we saw it here, but the values here, if I do T dot S13 OG slash dot theta goes to this particular value here. Actually, I want to go to this value here. Let's see what I get. See, 0, and then here are my sigma 1 and sigma 2s. So if I want to draw my 3D Mohr circle, I need to look at and determine what is my sigma 1, my sigma 2, my sigma 3. So my sigma 1s, I'm going to have to find the largest sigma 1. So for this plane, it was sigma 1 is equal to 37, sigma 2 is equal to 0. For this plane right here, it was sigma 1, oops, let's kind of write it over here. My sigma 1 was equal to 28, and then my sigma 2 is equal to 0. So what was my largest sigma 1? 37, 28, or, let's go here, 45.36. So that's going to be my largest, that's going to be my sigma 1 value. So 45 point something. So sigma 1 is equal to 40 point something something. Now I need to look through my sigma 2s. What's my largest sigma 2? 0, 0, but over here I see 19. So that's going to be that. So 19 something. And then what's my smallest sigma 3? It's just going to be 0. So I'm going to draw this as sigma 1, sigma 2, sigma 3, draw, draw, draw. That's it. That's my 3D Mohr circle. And I confirm that by looking if I can create, let's go ahead and look at it right here. I can confirm that by drawing and actually figuring it out. So if I do my stress equals 28, 0, minus 12, I do 0, 0, 0. If I do minus 12, 0, 37. So let's click that here. So if I do my eigenvalues, my stress, oops, let's look at this numerically. And what do you know? The same values pop up. So that's it. So we've got 3D Mohr circle, and we got those values. So the next question asks us, the material above is actually SR16. And we're looking at SR16, we're kind of seeing when it yields. So if I look at the yield point right here, it's probably about like 2.5 MPa is my yielding, sigma y. So my yield strength is approximately 2.5 megapascals. So sigma y MPa. And then we need to figure out, is it going to yield via von Mises, Tresca, or Rankine criteria? So let's remind ourselves what these different criteria are. So if we go all the way back to kind of our notes into the right before our yielding elasticity. So Rankine is sigma 1 greater than sigma y? So remember, this is 45 kPa. So is 45 kilopascals greater than 2.5 megapascals? No, that's not the case. What about Tresca? So Tresca is sigma 1 minus sigma 3. Well, sigma 1 minus sigma 3, nope, that's not greater than 2.5 megapascals either. What about this one? So I'm going to define sigma 1 equals this. We can look at this numerically. Times 10 to the 3. My sig 2 equals this. Again, these are kPa values. Times 10 to the 3. And my sig 3 is equal to 0. So now I can figure out what's my sig effective. It's going to be square root of 1/2 times sig 1 minus sig 2 squared, oops, plus sig 2 minus sig 3 squared plus sig 3, oops, sig 3 minus sig 1 squared. And here. So this would be my sig effective. And again, my sig y is equal to 2.5 times 10 to the 6. So my question is sig 1 greater than sig y? False. Sig 1 minus sig 3 greater than sig y? False. Is sig sig effective greater than sig y? False. So none of them yield. And it makes sense because, again, our stresses were kPa and our yield stress was megapascals. So a little bit of a tricky problem. Not tricky, but just one of my nonsense problems. Or not my nonsense problems, but you all know my style. All right, so let's look at the figure below where we have this essentially a cubic mold. And it's open at the top and the bottom. And so it can expand freely in 3 directions. And I'm working with a ceramic that's tungsten. I want to apply a large enough force to reduce the thickness in that direction from 1 meter to 0.99. Write the full stress and strain tensor. Give me the force required for this 1 meter cube. You can assume that the walls are rigid and immovable for this mold. And additionally, we said that we're well lubricated. So we have our coordinate system. So let's write out what's our stress tensor here. We're also given that this material is tungsten. So our Young's modulus, let's say it's around 300 gigapascals. It's ceramic. Poisson's ratio is 0.2. So I'm going to go in and start to kind of calculate this values. So I'm going to quit everything. So for this problem, say y is equal to 300 times 10 to the 9. I'm going to say that my nu is equal to 0.2. And that's good so far. Pretty good work. So what are the stress values that I have in this problem? Well, for sure, looking at it here, I've got a stress in the 1, 1 because I'm pushing in that direction, and it should be negative. Because it's well lubricated, all my off-diagonal components are 0. Now, do I have a stress in the 2, 2? We're open at the top, so this material can expand as we push. So we're pushing it in, this material in the 3, 3 can expand freely. So if it can expand freely, there's no force being applied there. So this force in sigma 3, 3 is 0. But in the 2, 2, these walls are immovable. They're rigid. So even though this material wants to expand, it can't. So I have stress in the 2, 2 direction. And now for my strain tensor, I know that, well, all the off-diagonal components are, 0. I need to kind of draw this out. So I know that there's a strain in the 1, 1 direction, and specifically, we have a cube, and the initial length or side is 1 meter. And in this direction, we are changing it from this initial length to a length of 0.99 meters. So my strain in the 1, 1 is just going to be simply the change in length over the original length. So it's going to be equal to final length, 0.99 minus 1 divided by 1. So I can solve for that a little bit later, dimensionless. What about the strain in the 2, 2? The material wants to expand, but it can't because the walls are rigid. And finally, there's going to be some strain in the 3, 3. So what are my unknowns? I know this guy, but I don't know this, this, or this. So I need to write some equations that I could solve for this. Well, I know that epsilon 1, 1 is equal to 1 over E times basically sigma 1, 1 minus nu times sigma 2, 2 plus sigma 3, 3. And I can start to kind of solve those values. So I'm going to solve this in Mathematica. So I know that my E11 is going to be equal to 0.99 minus 1 divided by 1. Again, this should be negative because we're in compression, so we're good there. I know that my E22 is going to be equal to 0. I don't know what my E33 is, so that's an unknown. And I also know that my sig 33 is going to be equal to 0. So now I could solve for my 3 unknowns. I need 3 equations. So E11 equals 1 over y times sig 11 minus nu times sig 22 plus sig 33. So I have that. Now let's do for these other values. I'm going to do double equal sign so I can actually solve this problem. There. And I want to solve this for close it sig 11 because I don't know what that is. I don't know what sig 22 is, and I don't know what my E33 is. I'm pretty sure. Let me check which I get. That's one of my unknowns. So I know what E11 is. I need to figure out what's my E22. I know what my E22 is. E22. Oops. E22. Let's set that double equal. Let's set that double equal. And then this is going to change to sig 22, and then sigma 1. So sig 33. This is going to be sigma 1. This is going to be 33. This is my 33. So solving for all of those, and we get our values. So let's see if this makes sense. So this is negative, we're compressing. Excellent, makes sense. In the other direction, again, we're compressing it. The material wants to expand, and the 3, 3 is expanding. So this seems to make sense to me. I like it. I'm happy with this solution. So that's pretty much what we've got here. So yeah, I think that's pretty much all the problems. And you can also notice that this is a principal stress plate problem. So assume the wall is rigid. All right, next question. So problem 6. Stopping an engineer, going to be a balloon, carnival clown, much better career path. No, engineering's the best. And so I'm going to do basically blow up these balloon animals. So I'm going to make an anaconda because I'm not talented yet at it. So it has a length of 25 feet. Diameter, thickness. What do I do right now? I need to see if this is thin-walled. So is R over T greater than or equal to 10? And I'm going to draw my thin-walled pressure vessel. This is my coordinate system here. I'm going to call this 1 and 2. So let's see if R over T is greater than or equal to 10. So I'm going to clear everything. And it says that I'm blowing up a balloon as well. So balloon is made of rubber. Rubber is a polymer. So my Young's modulus here is going to be 1 times 10 to the 9. That I'm approximate. Nu is going to be equal to 0.4. And then I also know that my radius is equal to, so the diameter is 12 or 1 foot, so 12 inches. So 6 inches is my radius times 0.0254 to get that into meters. My thickness is equal to 0.01 meters. What's my R over T? What do you know? Greater than or equal to 10. So we're good. So once we have the thin wall pressure vessel, we know that my stress tensor and the way that I've set up this equation is going to be my longitudinal here, my hoop here, everything else is 0. And I look at my strain, so I know I'm going to have hoop strain, which is going to be 1 over E times sigma H minus nu sigma L. I'm going to have longitudinal strain, which is 1 over E times sigma L minus nu sigma H. And I know that my sigma H is equal to delta P R over T, and that my sigma L is equal to sigma H over 2. So with that in mind, I can start to kind of, again, write some of these values down. I don't need my LaTeX, not yet. We haven't written the exam just quite yet. So sig H is equal to del P times R over T. Sig L equals sig H divided by 2. And then I also know that my E sub H is equal to 1 divided by Y. Actually, we'll save that for later. So, all right. Actually, let's just, yeah, we'll save that for later. All right. So now the last part of this question is blowing up my balloon takes a significant amount of strain, at least 100%. What will be the maximum pressure that I will have to blow in my balloon in order to make this balloon animal? Well, I know here that my hoop stress is my largest stress. So therefore, to blow up the balloon animal, the hardest strain is going to be my epsilon sub H. So my epsilon sub H must be equal to 1 in order to blow this balloon animal up all the way. So I'm going to solve that my strain of 100% is 1. E sub H is equal to 1 over Y times sig H minus nu times sig L. I'm going to solve for del P. There we go. This is my del P for the given, essentially, parameters of this problem. So there we go. This is my del P. So it's basically 82 megapascals. So I got my del P. I'm going to go ahead and kind of define this. So this is my del P. P equals, P, yeah, equals this. So 8.2 times 10 to the 7. So what's my sig H? What's my sig L? All right, what about my EH? We know that's 1. EL is equal to 1 divided by Y. 1 divided by Y times sig L minus nu times sig H. Nu times sig H. And there we go. 0.125. There we go. We got it. That's it. So stress strain tensors, turns out my lung will only allow me by 100 megapascals. Completely fine, right? 82, I could just make it. What about the rotation to get into principal stress state? No shear stresses, we're already in principal stress state. To get maximum shear, 45. Just like we've done previously. Great. Now, let's look at this below. Stress strain curves below are from the same material, but they've been processed differently. So, same material, processed differently. If the strengthening mechanism is work hardening, rank the density of dislocations. So, all right, if we're work hardening, we know that sigma y is proportional to the density of dislocations to 1/2. So the highest yield strength is A. So A has the highest, then B, then C, then D. So D has the lowest amount of dislocations. If it's been annealed, rank the time and temperature at which they're annealed. So we know that when we anneal at large times, high temperatures, our grain size, dg, increases, and the density of dislocations decreases. So A is the lowest time. So time lowest, temperature lowest. Then as we go here, this has the highest temperature, highest time. Because again, this kind of scaling parameter. So let's go look up. If grain size strengthened, rank the grain size. So similarly, for grain size strengthening, we know that sigma y is proportional to gg to -1. So we know that dg, actually, I'm sorry, dg of A is smaller than dg of B, C, D, et cetera, et cetera, et cetera. So D has the largest grain size. All right. And then if precipitate strengthening, discuss the relative volume fractions and size of the precipitate particles. So for grain size strengthening, we know, or actually precipitate strengthening, excuse me, that at some critical radius, r star, we're going to transition from cutting to bowing. So we cut on this side, we bow on this side. Why? Creating surface area is minimal, our energy penalty is creating surfaces. That's reduced at small radii bowing around. So perhaps this is A, and then B and C, and you could kind of rank them any other way. And the key thing is we know if we increase, our volume fraction of our particles increases, this shifts to the left. If VP decreases, it's going to shift to the right. Excellent. So 8. Label the deformation mechanism maps and which map is A, B, or D, and justify. What strengthening mechanism was used on these maps? So you've seen a similar map than this before in our in-class activity, so I'll kind of direct you to that problem. So this is TS, this is dislocation glide, this would be TS, dislocation glide, this would be elastic, this would be hard lock creep or DLC, Navarro herring, global creep, Navarro. So those are the values that we would get. We can also see here that the yield strength, this is the highest, lowest, or this is the highest, second highest, and lowest. So we're asked to look for basically A, B, or D. So we know that A, B, and D, D is the lowest. So this is going to be D, this is going to be A, this is going to be B. And what we can see changing here, similar to our in-class activity, you can watch that video, is that A must have the smallest grain size because we know that Coble creep DG scales to the -3. So it's going to scale with, again, you can kind of watch that video for a more thorough analysis. But yeah, so that's 8. So finally, we're going to get to number 9. So you completed your work, navigation system on Boeing. Engineer 4, you see that there's some micro cracks approximately 1 centimeter in length in the titanium supports. So your A naught equals 1 centimeter. So equals 1 times 10 to the -2 meters. These supports are under a 100 megapascal stress. So their stress is 100 MPa during the flight. Fracture toughness, so our K1C is equal to 100 MPa meter to the 1/2. And a yield stress of this, Young's modulus of this. For the alley above this, the applied stress is cyclical, thus fatigue is a concern. And it's telling us that R is equal to 0. How many cycles before to failure should you cancel a flight? So if R is equal to 0, we know R is sigma min minus sigma max. So if this is 0, we know that the stress profile looks like this. Nothing flight, nothing here, and then this is 100 MPa. So let's go back through our kind of lecture notes. So we're given K1C. So let's go back to here. Let's go to the end. So you know that our K1C, we have an equation for our critical as a function of K1C. So I'm going to quit everything. So I want to solve, I know that my A sub C is going to be 1 divided by pi times 1 divided by pi times my K1C, which is 100 times 10 to the 6, because again, that was megapascal, or to the meter 1/2, divided by my stress was also 100 times 10 to the 6. I'll do that squared. Let's see what we got. Let's look at this numerically. Don't fail me now, Mathematica. Uh-oh. Let's see, it might be failing me. Oh, that's too bad. Well, you're going to see the quitting of Mathematica and then close the program. Sometimes it doesn't want to respond. That's why these live videos, recordings, I will not edit around this. You're going to get the full in-class technical issue experience. So let's go through it right here. So again, let's just try this one more time. So my A sub C is going to be equal to, basically you saw it as 1 over pi for this problem. So let's look at that numerically. So that's my a sub c. We also had my a sub naught was equal to, I think, 1 times 10 centimeter. Let's double check. Where are my micro cracks? Yeah, 1 centimeter. So my a sub naught is equal to 1 times 10 minus 2. And let's go ahead down here. We also have that c is equal to 10 to the minus 24. We have that m is equal to 4. And then we need to figure out what's our, how many cycles until to failure. So we have our n sub f equation here. So f, we're going to assume f is equal to 1. And our delta sig, because our sigma min is 0, is just going to be 100 times 10 to the 6. So let's do n sub f is equal to 1 divided by, and let's put this in here, c times f times delta sig times square root of pi, and then we're going to do this to the m power, and then here, and then we're going to multiply actually this whole thing by a sub c to the 1 minus m divided by 2 minus a sub 0, 1 to the, oops, let me move this over so you can see, 1 minus m divided by 2, this, put one more here, this divided by, let's see, it's on the 1 minus m over 2. So 1 minus m divided by 2. And let's see, we did little c. There, oops, there's a negative value here because what was my a sub naught? A sub naught is equal to 1 times 10 to the minus 2. So let's make sure that's fine, that's fine. And a sub c, let's double check here. What is m over 2? I think I've got a little bit of an issue here. So again, in our code, we'll figure this out, but don't worry. So this value here. So we know that this should be here. That's a positive. 1 minus this. So a sub c should be larger. Divided by 1 m minus 2. It's actually going to be a negative value here. And then the m value here. And actually, this is going to give us a little bit of a weird answer on this problem. But you can see it's basically going to be negative or 0. So again, there's a little bit, not really a typo necessarily, but if you do this, sigma max minus sigma min, you'll kind of get this value. But anyways, this is how essentially you would probe and actually solve this problem. So yeah, that's pretty much it for this question. So next time, again, get ready for your, let me make sure real quickly that we have all those. M is equal to 4. Yeah. So there's just a little bit. Again, this is how you would kind of go and approach the problem. It's kind of a little nonsense answer. So I'm going to be very intense in terms of how to grade this. But that's essentially it. So prepare for your exam, do well, and then I will see you all in the next video when we go through kind of some of our exam problems. So see you then. Thanks.